Alright, so today we're going to look at these reduction formulas. Sometimes called a recurrence formula as well, because we're basically going to create a recurrence formula like, where did we see it? Oh, I know where we saw it. It was when we were looking at induction. You remember we created ones where you used the term before? Same sort of idea. Very often integration by parts is used to find the formula. So you'll find that technique being used a lot. It doesn't mean it has to be used. Sometimes it is something else, but by far the majority of them are done by parts. So here's an example where I'm just starting off with the integral of x log x cubed from 1 to e. So what I do is we try and generalise it. We say, well, let's create a formula for this. So instead of saying the power is 3, I'm just going to call it n. And this will be, I'll call it integral n, so whatever the power is. If I do it by parts, the u becomes log x to the power of n, to u, n log x to the n minus 1 over x. To v is x, so v is a half x squared. So we get uv, so half of x squared log x to the power of n, minus v du, so n on 2, x log x, n minus 1. But you'll notice that my integral over here is pretty much the same integral, but the power has been reduced. But now I've got it as a formula, I can just apply this formula to get it down to something simple rather than to keep going by integration by parts over and over and over again. So they're good ones when the power, I suppose 3 is not that high a power, but when the powers are high, saves us having to do it again, 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 and again. So tidying that up, we get e squared on 2, because I can actually work out the first one. Log e is, of course, 1, and 1 to the power of n doesn't matter what n is. 1 to the power of n is always 1. And sub in 1 will log 1, 0. So I know it's e squared minus 2, and then my minus n on 2 integral x. Okay, well, we want to find I3. Ours is when it's equal to 3. So our integral is I3, but now using my formula I can say, oh, that's e squared on 2 minus 3 on 2, I2. But then I can use the formula for I2. And so I2 would be e squared on 2 minus I1. I1, well, that would be e squared on 2 minus I0. Now I0 is great because now I've got the log x to the power of 0, which is 1. And so my integral just becomes the integral of x dx. And integrate x, of course we get half x squared, sub in, and we get our answer. So that's where a reduction formula can be very useful. So as I say, rather than applying integration by parts over and over again, because we know it's going to generate a pattern, we create a formula for that pattern. Of course, the other way I could have worked out I3, notice how I've done it by going down to I0. Another way of doing it is building it up from I0. So I could have said, well, I0 is the integral of x dx, so I know what that is. And then go, well, I1 would be e squared on 2 minus a half I0, sub in the answer I just found for I0. Then I2, so basically it's just going the other way. Sub in what we just found for I1, I3, sub in what we just found for I2, and again we come up with the answer. So whether you work your way down from I3 or work your way up from I0, doesn't really matter. So to say, integration by parts, I don't know if that's a word, is the commonest way. Is that a word? Commonest? Commonest way of getting reduction formulas. But okay, it's not the only way of doing it. Here's cotan to the power of n. You remember with the tan powers one, we said we use the same technique every single time. So I'm going to use that technique. So in will be cot to the power of n. And we said, we looked at tan, but I'm going to pull out the cot squared. The cot squared I can change to cosec squared minus 1, which I then can break up into two integrals. I've got cot n minus 2 cosec squared, but the derivative of cot is minus cosec squared, so I can do a substitution there. And on the right-hand side, I've got cot to the n minus 2. So same integral, but I've reduced the power by 2. So let's do that substitution, and I get minus u to the power of n minus 2. And as I say, the other integral becomes I n minus 2. Let's work out the first one, and there's my formula now. I've got minus 1 on n minus 1, cot to the power of n minus 1, and then I'll subtract I n minus 2. So it's now asked us to find cot to the power of 6, or I6. Now another way I could have done that formula though. Interesting ones. If you're talking trig, and because trig identities involve squares, often it will reduce by 2, like we saw our one just did. Now, if you don't have to use parts, and we didn't have to in this one, you could try looking at and just investigating. Let's see what happens if I add or subtract in with 2 different. So I've said in plus 2. I mean, it could have just as easily been in minus 2, but differ by 2. So if I'd done that with the one we just looked at and said, oh, okay, well, let's investigate. In plus 2 would give me cot to the power of n plus cot to the power of n plus 2, which I could factorise to be cot to the power of n, 1 plus cot squared. 1 plus cot squared is, of course, cosec squared, and I now have it in the form derivative times function. Add 1 to the power over the power, and now I just rearrange it, and I get in plus 2, because I want the higher one on the left here, would be minus cot n plus 1x on n plus 1 minus in. So if I want a formula for in, well, I'll replace n with n minus 2. And so n plus 2 becomes n plus 1 becomes n minus 1, and n becomes n minus 2. There's the formula. It's just another idea. Okay, let's work it out. They wanted I6. Sub it in, I get minus a fifth cot 5 minus I4. I4, I get minus, but minus minus becomes plus. A third cot cubed plus I2. I2 becomes minus cot x minus I0. I0 is now good because, well, cot to the power of 0 would be 1, so it's just the integral of dx. Integrate dx and we get x. So a lot quicker than having to repeatedly go through all those powers to get to the final answer. Integration by parts, as I say, very common. Commonest, even. Is that a anyway? So sometimes we use parts together with other ideas. So algebraic manipulation, trig identities, whatever. So this third example here, we've been told that in is representing the integral of 1 plus x squared to the power of n. We want to find a reduction formula, and they've given us a hint telling us we're going to reduce by 1 with this one. It's going to connect in with n minus 1. Okay, so I've got 1 plus x squared to the power of n. If I do parts, I'll get that du is 2nx, 1 plus x squared to the n minus 1. To v will be dx, v will end up being x. So I'll have uv, x times 1 plus x squared to the power of n, minus v to u. I'll pull the constant out, so minus 2n, x squared, 1 plus x squared to the n minus 1. Not quite my integral, but now I'll use the algebraic manipulation. So I want to create the 1 plus x squared there. So I'll say, okay, I'll make it 1 plus x squared minus 1, split that into 2 integrals, and we get x squared plus 1 x squared to the power of n, fair enough. Then we have minus 2n, 1 plus x squared times 1 plus x squared to the n minus 1, plus then 2n, 1 plus x squared to the n minus 1. Well, 1 plus x squared times 1 plus x squared to the n minus 1 is 1 plus x squared to the power of n. Now I can replace those integrals with well, the first one would be in, the second one would be n minus 1. So we have our formula. Mind you, it's probably better to make in the subject of this, so let's move the 2n in over to the left-hand side, and we get 2n plus 1 in, divide by the 2n plus 1, and we have a lovely formula to work out our integral. Okay, let's have a look at some HSC ones. 1987. They've told us it's the integral of cos to the power of n. They've told us the formula, which is nice, because if we can't get the formula, at least we can then use it to complete the question and pick up some sort of marks there. Okay, so in is the integral from 0 to pi of cos to the power of n. Cosine. Well, I don't know whether it's odd or even. Remember we had different techniques for odd and even. So I'm pulling out the cos, and then I'm going to do it by parts. Because I really don't know. Is n odd or even? So I don't know which technique to use. So I'm going to do it by parts. Du ends up being that lovely expression, minus n minus 1 cos n minus 2x sine x. Du is cos x v becomes sine x. So we get uv. Look at this closely. I'm going to sub in pi on 2. Well, the cos of pi on 2 is 0, so that's 0. And then I'm going to sub in 0, but the sine of 0 is 0. So that part there just is 0. So really, I've now just got my integral. n minus 1, the integral of cos n minus 2x sine squared. The sine squared I'll change to 1 minus cos squared. And now I can split that up into two integrals. And I've got n minus 1 cos n minus 2. Well, cos n minus 2 would be I n minus 2. And cos n is I n. So we're almost there. We've got to make I n the subject of this. Move that over. We get n lots of I n is n minus 1 I n minus 2. Divide by n. And we got the formula that they asked us to find. Oh, before I go and use it, let's show you that other idea. Oh, well, trig, I noticed their formula, it differs by 2. Maybe this is one I could use that idea with. So I n minus 2 minus I n would become cos n minus 2 minus cos. Cos n minus 2, 1 minus cos squared. 1 minus cos squared becomes sine squared. I've got u equals sine x. So u equals cos x. I've still got to do a substitution. And I've still got to use by parts. So did I really save any time this time? So it possibly wasn't a good way to go for this particular one. But anyway, let's keep going with it and show that it does work. So uv minus the integral of v to u. And I get 1 on n minus 1 I n. So playing around with that one, yes, we do get the same form. It looked like there's no way I could avoid the integration by parts. It didn't matter which idea I used for this one. Okay, let's go and find the I5 that they wanted. I5, 4/5 I3, I3, 2/3 I1. Now that's where I've got to stop, because remember this is being reduced by 2. I can't do I negative 1. So I1 would be the integral of cos x. And that's okay, I mean that's a simple integral. Integrate cos, we get sine. Sub in pi on 2, we get 1. Sub in 0, we get 0. So we just have 8/15 for our answer there. One a little bit more recent. I've got to show you this one, because you're going to love it. You really will. You know what's coming now, don't you? Okay, so In is defined to be the integral of tan to the power of n. And then they've given this other formula. The Jn is going to be minus 1 to the power of n I 2n. And that's for n equals 0, 1, 2, and so on and so on. So the first thing we have to do is show that in plus 2 is 1 on n plus 1. Well, in plus 2 is integral of tan to the power of n plus integral of tan n plus 2. Add those together, I get tan to the power of n, 1 plus tan squared. 1 plus tan squared is, of course, sec squared. And we've got to change the limits as well, of course. We get u to the power of n du, sub in 1, sub in 0, and there it is, 1 on n plus 1, which is what they want us to use. Deduce that Jn minus 1 is this expression. Okay. Well, Jn was defined to be minus 1 to the power of n I 2n. So therefore, Jn minus 1 is minus 1 to the power of n minus 1 I 2n minus 2. Okay. What I've done there, all I've done is I've tidied up the minus 1 to the n minus 1 so I can pull out a common factor, because notice how my answer, I want minus 1 to the power of n. So that minus 1 to the n minus 1, I've made plus minus 1 to the n. So I've got that factor. I've now got I2n plus I2n minus 2. Well, hang on. In the first part, remember, see they differ by 2? Well, in our first part we had a formula that differed by 2. I'm just going to use that formula that we just worked. So I'm going to let n in that formula be 2n minus 2. Sub that in then, and we get minus 1 on n to the over 2n minus 2 plus 1, which is 2n minus 1. A lot of time was probably wasted on people actually then going and working out I2n plus I2n minus 2, when in part A you've already found a formula for that, so you can save yourself a fair bit of time. Oh, look at that. We've got sigmas. Oh, how good is this question? So now we're going to show that Jm is pi on 4 plus the sum from n equals 1 to m of minus 1 to the power of n over 2n minus 1. So Jm. Well, Jm is equal to minus 1 to the power of m on 2m minus 1 plus Jm minus 1. That's coming from our previous part. And Jm minus 1 then would be minus 1 to the m minus 1 on 2m minus 3 plus Jm minus 2. And so on and so on and so on. And I could keep going till I get to J0. Well, have a look at what we've actually got here as far as this sum. And you'll notice it satisfies the formula in the sigma up here. If that's the general term, minus 1 to the power of n on 2n minus 1, notice the last term here, which is actually the first term written down, but the last term of the sum, well, that would be m, which is what we've got on top. The first term would be when n is 1. So we've got that part. Hopefully, when we work out J0, we'll get pi on 4. Well, J0 is the integral from 0 to pi on 4 dx. And so subbing into that, sure enough, we get our pi on 4. Oh, but it did not stop there. Use the substitution u equals tan x to show that in is equal to 0 to 1 of un on 1 plus u squared. Okay, in is the integral of tan nx dx. So they've said use u equals tan x. I'm going to rewrite that as x equals inverse tan of u for this one. And the reason I'm doing that is I'm keeping an eye on what I'm trying to prove. You see that 1 plus u squared on the bottom? I'm thinking, hang on, the derivative, when I differentiate when I differentiate inverse tan, I get 1 plus u squared on the bottom. So dx becomes du on 1 plus u squared. And change the limits, it now becomes quite straightforward. Because if u is tan x, then tan to the power of n is u to the power of n. The dx, I've now said, is du on 1 plus u squared. I need to throw some working out in there because otherwise it looks like I've just written the answer down. But there it is. There it is. All right. Why on earth did they ask us to do that? Because now comes the fun part of the question. Deduce that in is in between 1 on n plus 1 and then conclude from that Jn approaches 0 as n approaches infinity. Well, u to the power of n plus 1 on u squared, I know that's always greater than 0. Because remember, we're going from 0 to 1. So I know I'm substituting positive numbers into that. So I'm never going to get a negative out of that. So our integral then, the curve's always above the x-axis. So therefore the integral is always positive. There's the first part of my proof. The left-hand side here, quite straightforward to prove. Basically we're just saying, hey, this curve always above the x-axis, therefore its integral has to be positive. So we know in is always greater than or equal to 0. Now the right-hand side, proving it's always less than or equal to 1 on n plus 1. And we'll go back to this formula. In plus 2 is equal to 1 on n plus 1. Well, that means in is 1 on n plus 1 minus in plus 2. But hang on. Remember back here? We said in is always positive. Well, if in is always positive, then I'm always taking away a positive amount from 1 on n plus 1. Whoops, went the wrong way. So therefore, in has to be less than 1 on n plus 1, because I'm always taking away something from it. So there's the right-hand side of that inequality. So thus, we have trapped 0. Sorry, we haven't trapped 0. Thus, we have trapped in between 0 and 1 on n plus 1. Okay, they have asked us, hang on, let me go back to the question. What was it they asked us? Oh, there it is. Conclude that Jn approaches 0 as n approaches infinity. Okay. Well, as n approaches infinity, 1 on n plus 1 would be 0. So I've trapped in between 0 and 0. So it's fair enough to say I know that the limit as n approaches infinity of in is 0. But hang on, Jn was defined to be minus 1 to the power of n I2n. So if IN's approaching 0, I2N's approaching 0, which now means JN is also approaching 0. 2G is what we'll play with reduction formulas.